who represents quantum industry. Last week it was with Quantum Circuits Incorporated, now it's D-Wave.
Yeah. So I just put that there. There's also quite a lot of news about it.
So Nitish started as an algebra engineer. Then he did a PhD on qubits and quantum many-body physics in a really nice group at University of Maryland. And then moved on to a very different types of activity, which got him to demonstrating some of the highest fidelity, or maybe the highest fidelity gate operations on this unusual qubits, which we were just discussing. People tend to call them bosonic, but there's not much bosonic about them. So I think it's a fairly exciting news, recent results. So welcome, Nitish.
Yeah.
Looking forward to it.
Yeah, thanks, Vlad. I'm going to talk about demonstrating high fidelity operations in these new types of qubits that are called erasure qubits, and in particular dual rail qubits that are made out of superconducting cavities. And a lot of these kinds of hardwares are not too popular, and maybe most of you might not know about them. So one of the aims of this talk is to just introduce what are erasure qubits, for example, and how we are looking at it at QCI and D-Wave now, which is making it using dual rail cavity qubits. And the other thing is that I've put this asterisk here on the operations. Like most of the time when you hear about high fidelity operations, they're just blanket, just said that they're high fidelity. But in this talk, I'm going to take a different view on it. I'm going to take, I'm going to look at it through the purpose for which we are going to use these operations for. And for that, I'm going to look at it in particular for quantum error correction. And there are basically two reasons why I'm doing this asterisk thing. One is that most quantum applications require error rates that are 10 to the minus 6 at the minimum, and for applications like Shor's algorithm, they need to be at 10 to the minus 9 or 10 to the minus 12 even. And in any modality, the current fidelities and the gate operations are not good enough. They're orders and orders of magnitude lower than what is needed. So the only way that is known to bridge this gap is to do quantum error correction. So eventually everybody is going to do quantum error correction, so we might as well look at the operations through that lens. And the second thing, so that's why I'm going to look at all of the stuff that I present from the lens of quantum error correction. And so one of the biggest challenges in quantum error correction is the overhead. So basically you need to encode your logical information in a lot of physical qubits, and there is a lot of work going on to basically reduce this overhead of how you can encode this very fragile quantum information at very low error rates, but at using less number of physical qubits. And there are basically three parallel approaches to achieve this. The first one is quite obvious, is just design better error correcting codes. Design codes which store your information in a much more compact way so that you require much less physical qubits. The other is to design codes which have higher thresholds. And the threshold here, if you don't know, for the experts, thresholds are basically the numbers which I consider like a pass, fail in an exam. A qubit, when it is below the threshold, you can do error correction and you can scale the error correcting code and suppress your error rate to arbitrary low values, but it is above the threshold, then there's just no point. Yeah, it's never going to work. No matter how big a code you make, you're never going to suppress the error rates. So you just need to pass this thing, which is the pass-fail, which is the threshold, but if you pass the exam by a larger margin, you do a better job. So most of the time, these pass-fail rates are like 99%. Your qubits have to do stuff better than 99%, but if you pass this threshold by a bigger amount, you can actually do error correction in a much more less resource intensive way. The other thing which is also pursued everywhere, including our company and in the world, is like making better physical qubits. Basically, make your qubits so that they pass this threshold by a large margin. So increase the coherence times, make faster gates, and basically improve the noise in your qubit. This is basically one of the works that Vlad pioneered with fluxonium qubits to make better coherence times and faster gates, so that if you have error correcting code, it has a threshold, but your physical qubit can beat this by a big margin, so you can do error correction much more efficiently. And the last one is what I'm going to highlight in this talk, is maybe to use both 1 and 2 simultaneously. And how you can do that is basically co-design your physical qubit with the error-correcting code, such that your error-correcting code basically corrects for the types of noise that your qubit has much more efficiently, and it doesn't correct for the noise that your qubit basically doesn't have. So you don't need protection against that anyways. So that's kind of the approach that I'm going to talk about in this talk mainly. And this is actually not new, and this is actually being pursued by a lot of people around the world. And one of the most common example of this is like the Pauli noise bias, which is prevalent in the so-called cat qubits, which were the work was started in Yale, and now it's pursued by some companies like Alice and Bob, and even Amazon Quantum Computing. So the idea is to just encode your information in two very disjoint states of this oscillator, such that it is very hard for you to have bit flips in one direction, like the bit flips are exponentially suppressed, whereas you can have one of the kinds of noise, which is the phase flips. But because you have this large bias, what you can do is that you can only correct for the errors that happen, and the other one that are suppressed by your qubit itself naturally. The advantage of that is that in the limit where only one kind of error happens, you can just do a quantum repetition code instead of this 2D surface codes. But even when the bias is not infinite, you can get away by doing so-called rectangular codes, where one dimension which corrects for the errors that happen much less often is much shorter than the dimension of the code which corrects for the errors that happen more often. So again, this is a way to do it where you will have less resource-intensive ways to scale quantum error correction. And the one that I'm going to talk about today is that of another kind of bias, which is called an erasure to Pauli bias, which is to say that your Pauli errors happen at a given rate, but there is another type of error called the erasure error, which happens at much higher rate, but both of them happen pretty small, like at a very low value. But the predominant error is the erasure error, and that is much easier for your quantum error correction code to correct. So I will go into much more detail about this, but again, there are several platforms that are actually pursuing this. Some neutral atom platforms pioneered by the group in Princeton by Professor Jeff Thompson is pursuing it, and then again AWS Quantum is doing it using so-called dual-rail transmon qubits, but we at QCI are pursuing the one which is dual-rail qubits with the 3D cavities, and that's what I'm going to talk about today in this talk. Okay, so the rough outline of this talk is the following. In the first part, I'm just going to introduce erasures and what they mean for QEC, and how dual-rail cavity qubits make a good erasure qubit. The second part, I'm going to stress about how you can preserve this bias between erasure and Pauli noise all throughout your gates and operation, including idling. So how you can do that in every possible operation that you might ever want to do, and that's when it actually makes sense and it's useful. And the third one is sort of like a bonus if I have time, and then we can go to some very recent work where we are trying to demonstrate a very neat application of this erasure qubits in doing magic state preparation in a distance 2 surface code. Okay, so the way I like to introduce erasures is actually by doing some a classical analogy, and this is the way I think it makes it the most intuitive. So the way to understand an erasure is the following. First, let's look at just a classical noise channel, and let's say you are transmitting some classical information, and because you want to be robust against noise, you just copy your information, let's say 5 times, and send it to somebody who is decoding at the other end. So if you have this error channel which is bit flips, which is that randomly some of your bits can go from 0 to 1, and you wanted to send a 0, if 3 of your bit flip, then the person at the other end is going to think that maybe you were intending to send 1 because the majority is saying 1, so let's just assume 1. So what this means is that your decoder can get confused if there are 3 errors in this channel, and you will decode the wrong information. But if you had, let's imagine another channel where your bit doesn't flip, but it just gets corrupted so that the user knows that the other side, you don't get the other state, but you just get something that it says it's corrupted. It's not a valid information. In that case, if this was the only channel, if there were 3 erasures that happened, then the other person in the other end can decode this still and interpret it correctly that you were actually meaning to send 0. So to actually fail, you need to have like 4 of them, even like 5 of them, all of them have to fail. It's only then that the sender will kind of don't know what you're trying to send. Otherwise, they're perfectly okay to decode it. So the thing is that the erasures can handle almost twice as many errors as a bit flip channel can handle. And that's kind of the intuition of why erasures can be a better type of error. And this analogy actually goes exactly in the quantum domain as well. So for example, if you were trying to do a quantum repetition code, if you were trying to protect against bit flips or phase flips, you can only choose to do one or the other in a 1D code. And if you're doing that, if your predominant noise channel was this Pauli error, either Z or X, you can only correct for n-1 if you made a repetition code using n physical qubits. You can only correct n-1 by 2, but if you had erasures, you'll need all n of your qubits to fail for it to not work. n-1 are still fine. And when you translate it to the 2D, the most common code that is used in the industry, which is the 2D surface code, if you have a distance d code, a stabilizer code with a distance d can correct up to d-1 by 2 Pauli errors, but it can correct actually d-1 erasures as well. So this analogy from classical world translate exactly to the quantum world as well, actually, and that's pretty neat. And the other neat thing is that even if you had both types of errors, like Pauli errors and erasure errors, this works as well. So you will just be able to correct your Pauli errors at a much faster rate than you can correct for erasure errors at a much faster rate than you can correct the Pauli errors. Okay, so how does this work in practice? Initially, you might think that, okay, this error kind of seems like more disastrous in the sense that if my qubit just gets corrupted, I just don't know whether it's 0 or 1. This is actually much worse than having to flip from 0 to 1. But the trick is that each qubit now has a flag, and it tells you if it is corrupted individually rather than in an error correcting code where you cannot kind of probe each one of your qubit. The only thing that you can probe is like some joint parity. The joint parity, the decoder has to do some work to interpret sort of which error happens. So for example, in this code, if the joint parity operators of the two codes that are shown here, for instance, if these two flip, your decoder sort of has to do some work to find out, okay, this is the qubit that is probably corrupted, that's why these two flipped. Whereas for erasures, each one of your qubit is going to raise a flag when it is corrupted. So the advantage of erasure comes from the fact that you don't know what error happened, but you know exactly which qubit was corrupted rather than interpreting it through the decoder. So you have so much more additional information that each one of this qubit can tell you two things. First, the ancilla qubits will tell you what are the joint parities of your code, whereas each one will also tell you whether it is corrupted or not. So this additional information actually makes it so that you can correct many more erasures than Pauli errors. And you can also see this in simulations. So if you simulate a surface code under just Pauli noise, you'll see that the threshold, which is what I call the pass-fail criteria, is by 3%. So you have to be better than 3% in your Pauli rate to do effective error correction, and the further away you are from this threshold, the further beyond you are, the less resources you will need to scale the surface code to get a given logical error rate. And if you have erasures, you look at that. That is a much easier exam to pass, so to say. So because you only need to get 75% to pass, so it's much easier to pass this exam, and you can also pass it by a much bigger margin, and the reward is also actually higher because you look at the exponent and the logical error rate, the exponent is double. So you scale this the logical error much faster in the presence of erasures than in the presence of Pauli noise.
Okay. 4.8 is what, fundamental constant of nature?
No, it's just some simulation.
Okay.
It's basically the simulation is also not very it's not very detailed, but the way that the simulation is done is that for every stabilizer round, you just put in some probability of each qubit getting erased, and then you just do some Bernoulli trials, and then you see how many times do you fail and how much does your logical error rate go down. If you're at what rate does it never go down, which is basically this. If you inject this erasure error at 24.8% of the time in this code, then it will just never reduce. But if you do it even a little bit smaller than that, then it will reduce. So it's kind of like a numerical thing. Okay, so finally I'm going to talk to you about what does it mean to make a good erasure qubit. So again, like I was telling you, the idea is to have your noise in your qubit structured such that the most common error that happen in your qubit is the most easier for your quantum error correction code to correct for. So we call this jokingly the Puri pyramid because it is Professor Shruti Puri who introduced it, and it's kind of like green are the erasures, which is like this is the type of error that your error correcting code has the easiest time of correcting. So if you can manage that, if there are errors in your qubit, these are these type, then it is much better for you. The next one that you can have is the Pauli errors, because that's what your error correcting code, for example, the surface code is trying to correct for. It's trying to correct for like X and Z errors, and that's why you have this 2D grid. So that is still okay because you designed your error correcting code to do that. And the worst kind of error is the leakage, because the error correcting code doesn't know what to do with it, because it is assuming all your qubits to be perfect two-level systems. So when you get a state that is not even in your computational state, it just gets very confused and it's pretty bad. So what you want is you want your main errors to be the erasure errors. The next source of noise should be your Pauli errors. The worst should be erasures. You should basically never have them. And the trick that erasure qubits play is that actually every time you get this erasure state, you're actually leaked into a non-computational state. But if you have a gadget which kind of just tells you whether you are out of the computational space or not, and it only tells you that and doesn't disturb your information if it is in the code space, then you have basically converted all of the worst kind of errors into the best kind of errors. And that's the idea of erasure qubits. They have an ability to have the most common type of error, a leakage out of the computational state, but in addition to that you have a gadget to basically convert the worst type of error to the best type of error. So the only way now you have the worst type of error is that when your gadget fails and erroneously tells you that you are in the code space when you are leaked, which is a missed leakage. So it's again a double error. First you have to leak, and then you have to also miss detecting it. So that's kind of the idea of why erasure qubits are supposed to be better. And why can we make it better using dual-rail cavity qubits is the following. So let me first introduce to you the encoding. So we encode information in this joint single-photon subspace of two detuned cavities. And these are 3D cavities. You can see here post cavities. And the information is just in which cavity the photon is. Is it in the left one or the right one? That's kind of the logical states. And the dominant error channel that these cavities have is just leakage to the vacuum state. Because if you lose a photon, no matter from which cavity, where you're going to end up is the vacuum state. You're going to end up in the 0-0 state. And the other noise, which is the dephasing, is inherently suppressed because you see these are just hunks of metal. And the frequency of these metal objects are only defined by geometry. So we should inherently be suppressed to have any like phase noise or Z noise. And there is basically no way to get a T1 effectively, because the only way you can swap a photon from 5.5 gigahertz cavity to a 6 gigahertz cavity is you leak to vacuum and then you heat to the other side, because you can't just convert this photon. There are like special nonlinear elements that are needed to convert this photon. You can't just do it for free, so to speak. So that's kind of the reason why dual-rail cavity qubits make really good erasure qubits. And yeah, so here's like a more quantitative example of that. So the T1 error in these kinds of cavities reaches about a 1 millisecond rate, but the T5, which is the dephasing, can be like 1 order of magnitude higher. And again, the thermal population can also be very, very low. In our devices, we measure about like 0.1%. So the chance of decaying from one cavity and then heating on the other is basically non-existent. We can't measure it. So that error is just never happens. The other error that happens is the dephasing, but happens at a much slower rate than the dominant error, which is the leakage to vacuum, which is an erasure. Yeah, and you are not limited in principle to make it out of 3D cavities. You can even make it using 2D structures. And one of the things, the next point is where I'm going to get into a little bit trouble with Vlad, so I'm going to be careful, is like, the claim is that you can always make this almost as good as you can make any qubit with Josephson junctions, because those are harder. and these are just cavities. And Rob likes to say that if you can make a fluxonium qubit with 1 millisecond coherence, you should be able to make it also in like a 2D planar structure, and you don't have to do the 3D cavities. Okay, so that's kind of why we can do erasure qubits using cavities very well. And yeah, and finally I want to summarize this part by again going through all types of errors that are going to happen in my qubit and how do they scale and how are they classified into these 3 blocks that I've shown here. So the first one, like I said, if you have information in the cavity either in the left or the right, the dominant thing that happens, which also happens not that frequently, is the leakage to vacuum, and that happens at the rate of like 500 microsecond to a millisecond. The next dominant error that happens is dephasing, which is the frequency jitter of this cavity, and this happens at the time scale of about a few milliseconds. And finally, the bit flips, like I was saying, they just don't happen. Here I've put a greater than sign because we just don't know the actual number, we can only place some bounds on it. Okay. Finally, I want to say that dual rail qubits are not new, at least the encoding. They've been around for quite a long time. Like, I think they were first introduced in 1995, and then there have even been proposals in other superconducting and atom-based platforms to do it with. There have been several proposals with transmon-qubits, some with fluxonium qubits, and also with atoms and other architecture. So this is the idea of dual rail qubits is definitely not new, but what is new is sort of leveraging it to do better quantum error correction. Okay, this is kind of the end of the first part of my talk, so I want to pause and see if there are any questions at this point. If there are any, I'm happy to answer, or I can move on to the next point. Okay. So the next part of my talk, I'm going to go through all the gates and operations that you need to do, and you need to preserve this bias between erasure and Pauli noise all throughout your gates. So this is one thing that people don't really appreciate, is that it's not enough for your qubit to have this bias while idling. You also need to preserve it while you do all your gates and operations, and that's when the thing is actually useful. Okay, so like when you want to do quantum computation, you need like this checklist of operations that you need to perform. One is just the state preparation, measure how good your coherences are, measure it, do single qubit gates, 2 qubit gates, and then this new gadget that I talked about, and then some reset. But this talk, because of the time, I'm going to concentrate on the 3 most primitive operations, which is measurement, single qubit gates, and 2 qubit gates. And to do that, I'm going to introduce some more parts of the hardware that we use to do them. So, like I told you, the dual rail qubit is encoded in this single-photon manifold of 2 detuned cavities. But in order to do these gates and operations, we attach some nonlinear elements to it, and they are the following. The first one is what we call a measurement transmon qubit. It is the one that is used to measure whether a cavity has a photon or not. And there is also a coupler in the middle, which is used to perform like the swaps between the two cavities, which is the single qubit gates, which also I'm going to talk about later. So these are the other peripheral modes that we have to introduce to do gates and operations. Yeah. So the first thing that I'm going to discuss is how do you measure these qubits. So it's kind of not that hard, but the only thing you need to figure out is that is there a photon in your cavity, and if there is one, is it in the left one or is it in the right one? And this can be done pretty easily by this coupling transmon, because you couple your coupling transmon to the cavity, and they have what is called as a frequency shift depending on the population in your cavity, and then you can do like a controlled pi pulse on one of the transition, either when you have a photon or you don't have a photon. And when you do that, you can see that you can get a pretty good discrepancy. Like, for example, if you perform the pulse at the frequency shown here, the one when the photon, there is a photon in the cavity, you will either excite the transmon if there's a photon, or you will not. And that is basically, you have mapped the population of the cavity onto the transmon, and then you just measure the 2 transmon, and you correlate the 2 measurements. So what you get by doing this measurement is that you can get this 4 physical outcomes. You can get either 0, 0, 0, 1, 1, 0 or 1, 1. So you actually get this erasure check for free. So when you measure your circuit at the end of the line, you know whether you are in the erased state or not, and if you're not, you get to know whether you're in the left or the right cavity. And the way we benchmark this thing is the following. We just prepare all of the 4 physical states in this dual rail qubit, and then we measure. We apply this measurement protocol, and we just look at how often we measure the correct state. And what the key thing that you have to take into account is that we measure a logical misassignment rate at about like 1 e minus 4, which is, and the reason for that is that if you look at it, you need to have 2 errors to misassign a logical 0 or logical 1. So even if one of your measurement failed, you will erroneously just think that it is an erased state, but you will never think it's the other logical state. So that's kind of why, without doing anything very special, we can get a logical misassignment rate of like 1 e minus 4 almost. The second error that happens is that you are in the code space, but it erroneously tells you you are in the erasure state. And this is a much less damaging error, so to speak, because you just assume something was error when it was not. The reverse is the worst kind of error. You don't want to ever confuse an erased state for a state in the code space, and that happens at a much smaller rate. And actually, these are numbers that are kind of 2 or 3 years old. By this time, we have even reduced the erasure rate to about 1%, and the leakage reduction rate to be better than like 0.1%. Okay. And the other neat feature of this thing is that because this measurement is highly QND, you can just repeat it many times and not only correlate the measurement between the 2 cavities, but also correlate with the number of rounds on each cavity. And you can suppress this thing even more with an additional cost of assigning erasures much more often if you are in the code space. So that's the cost, but the benefit is that you suppress the logical misassignment rate and the leakage detection error rate by by exponentially, basically. So that's kind of the measurement. The second thing I want to talk about is the single qubit gates. The single qubit gates in this architecture are just basically swapping the photon between the 2 cavities. And this we accomplish by just modulating the frequency of this coupler here at the frequency which is the difference of the 2 cavity frequencies divided by 2. And we just enable a parametric process, which in the dual rail block sphere is just like doing a Rabi rotation around between 0, 1 and 1, 0. And the data that is shown here is just the population in one of the cavities as a function of the drive time of this pulse. And what you see here is like you see almost unity contrast oscillations between population of one cavity and the other. And the other important thing to note here is that there is this decay is kind of asymmetrical. From the top, it is much more is much rapid than from the bottom. And the reason is that the top decay is dictated by how fast you lose your information, like lose your photon to vacuum or something. And what is the bottom one is when you lose whether it is in left or the right cavity, which is dephasing. Whereas the top one is the erasure. So you see the erasure is still dominating. So you can say that you can already tell that this is going to be much better if you detect these erasures. And this is exactly what we do. The other thing I want to point out is these oscillations can be really fast. This is like 100 nanosecond gate with a coherence time of a qubit, which is like around 5 to 10 milliseconds. So already you can see that the gates are going to be pretty good. And so the way we benchmark this is to do RB. And we do RB in 2 ways. In the first way, we don't detect for these erasures, and we just do the RB like a normal qubit. And when you do that, you see that you have an RB infidelity already better than 3 nines. But then if you remove the dominant error source, like basically you remove the shots where you detected an erasure and only keep the shots where you did not, you can see that you can boost up this fidelity by like almost an order of magnitude. And this is again telling you that your dominant error source during this gate is actually the erasure error, because if I post-select it, my fidelity of this operation goes up. That means that the dominant error rate is the erasure rate, which is what we wanted to have in the first place. And again, these numbers are kind of old, like 3 years old at this point. You can add one more 9 in the middle for both of these things and it is still true. So the fidelity that we very commonly measure now in the lab is like approaching 5 nines almost. Because you can even see it from just the gate time and the coherence times that I mentioned. Okay. Yeah, so the other thing that I want to point out here is that the single qubit gates are the only thing that prevents right now for cavity qubits to not be used in a linear repetition code, because when you drive this thing, you convert a phase flip between the two cavities into a bit flip, because if you lose the phase of your drive, you will now swap the photon incorrectly and it will become a bit flip. So the fact that this gate destroys this bias between the X and Z is why you can't just have like a repetition code with cavity qubits. If this was true, then you could just do what like AWS and Alice and Bob are trying to do. You can just build like a repetition code and this would be fine. Okay, so finally, one of the things that I want to talk about is the most non-trivial thing that all architectures have to engineer, which is a 2-qubit gate. So, and the thing that we want to, again, the thing that we want to achieve with this 2-qubit gate is, first we need to preserve this error hierarchy that I told you about with other operations. You want the erasure errors to be dominant. Second, you need it to be fast as compared to the coherence times of the dual rail qubits that I mentioned. And then you want it to be really simple so that it's not a big challenge to kind of tune it up and work with it. So these are kind of the wish list of the operations you might want to have. And the neat thing about dual rail qubit is that you might think that, oh, you have these 4 modes and now you want to entangle these 4 modes, so you probably have to engineer some 4-body interaction. But that's actually not true. It is sufficient to just entangle the middle 2 qubits, like one cavity from each of the qubits. And when you do that, you can already entangle the whole 2 dual rails. And that's what I'm going to show in this, in the next part of the talk. So the gate sequence is very simple, and we have very cutely named it as swap weight swap, because that is exactly what you do in your gate. The thing that you do is you have 2 qubits here. Notice that I have labeled one as control and one as target. Although if you try to make a CZ gate, you can see from the unitary there is nothing special about one or the other. But the way we are doing the gate, you'll see that one is a little bit different than the other, and that is actually not a bad thing, that's a good thing. So the way we do it is that we take one of the qubits, which I call control here, and we swap a photon from cavity A2 into the coupler mode C here, which is a transmon-like mode in the middle of the 2 cavities. And this is the same kind of pulse that you use to do single qubit gates. We use the same kind of pulse to, instead of swapping from, let's say, a cavity A2 to B1, we swap it from A2 to C. And what this does is that there is an always on cross-current interaction between the coupler mode and the 2 cavity modes, but it's always off because there is never 2 photons simultaneously in the mode C or A2 or C or B2. But by doing this swap, you're kind of creating a state where there is simultaneously 2 photons in C and B1, and that kind of switches on, so to speak, through a microwave pulse, an interaction that already always existed but was off because of the encoding, but now you turn it on. And you do this, you turn it on, you entangle your qubits by this cross-current rate, so you acquire a Z phase because both these modes have now shifted in frequency because of this cross-current, and you wait for an amount of time so that you acquire a pi phase, and then you just go back to where you were. And this basically engineers a control Z operation, because only one of the 2 logical states in your, one of the 4 logical states in your 2-qubit manifold is going to attain this phase, because you simultaneously need a photon in A2 and B1 to switch on this interaction between C and B1. Otherwise, this interaction is just off for all the other states. And you can see it from this diagram here. There's only one state, which is the middle one, the second one in here, where there is simultaneously photons between the middle mode and the right mode. There is no other state that does that. So you just get a very clean CZ using this kind of protocol. And the sequence is also basically trivial. You just put a Gaussian flat top pulse to swap it, you wait for some time, and you do another reverse pulse, and then you're done. And let me tell you some numbers about it. So you kind of switch on an interaction at the rate of about 1.5 to 2 megahertz. So you can do this gate completely in like about 500 nanoseconds. And again, you need to compare this number to the lifetime and the coherence time of the dual rail cavities, which is like a few milliseconds already. And the other thing that is concerned is like because you have this nonlinear coupling element between cavity A2 and B1, there is always an always-on interaction between A2 and B1 as well, which just exists even if you don't do the swap, which is the residual cross curve between these two cavities. But this is like more than 2 orders of magnitude lower than that. So the on-off ratio of this gate is also pretty good. Okay, so yeah. And how do you benchmark this? So one of the ways we have benchmarked it, actually we have benchmarked it in several ways, but one of the ways we have benchmarked it is to create like a fully entangled state between these two dual rails, and then you just repeatedly entangle and disentangle your qubits, and then you, at the end of that, you just do a state tomography, and then you try to see how good of an entangled state you've created at the end of this sequence. And you can do this by reconstructing your density matrix by doing just this very common state tomography. And what you see is that as you do more and more of your CZ gates, the fidelity drops, but it drops very, very slowly. Like already with like 27 gates, look at the fidelity that has dropped. It's basically not even dropped 1% when you've done like 25 of these gates. So the fidelity of this gate just by itself is pretty good. And now, because these are dual rail qubits, I have to discuss 2 error rates. The first is how often do you get erasure every time you do this gate, and how often do you get like this Pauli error. So you see the erasure rate is already like 0.5%. This is in competition with actually the total gate infidelity of most of the other people. But this is actually a post-selectable and a correctable error. So this one you can just take out. So if you post-select that and look at the state fidelity, you see that it drops by almost 1 order of magnitude lower. Again, this demonstrates that you still have this noise bias between Pauli noise and erasure noise. The erasure noise happens at a low rate, but the Pauli noise happens at even lower rate. So we already checked this box of preserving the error bias during this 2-qubit gate. So basically this makes it so that you have preserved the error bias in all of the gate and operations that you can do. The other thing that I'm going to tell you about this gate, which is non-trivial, is that apart from this Pauli bias, there's also a lot other structure in the errors that happen in this gate, and that can be leveraged quite a lot in error correction context. So first I want to see like what do you expect just from the sequence, like intuitively. So one of the first things that you can notice is that the cavities A1 and B2 just don't participate in the gate. They just are idling all the time. So there should be no way for you to swap erroneously an excitation from A2 to A1 and B2 to B1. So the bit flips should still be very, very suppressed in this interaction. You should just never have bit flips, just like you never had bit flips when you kept your dual rail idle. So that should be preserved. The second thing is that this gate is kind of excitation preserving, which is to say that you swap your information into this lower coherence transmon mode, but every time you lose an excitation in that mode, it's a detectable error again, because if you left your excitation when you're swapping from A2 to C, inside of C, when you measure your dual rail qubits, you will find the red qubit to be empty in vacuum. That means that every time you mess up your swap or something, that's not a problem in the Pauli error. It is just an erasure again. Because if you mess up the swap and don't bring it back correctly, you are still erased. You don't have a Pauli error. You can post-select for that. And the third thing that I want you to notice is that the target qubit, the blue qubit here, is just doing nothing. It's just idling the whole duration of the gate. So again, all of the errors that happen for the target qubit should basically be the idling errors of the dual rail qubit. There should be no additional error that you should get on the target qubit, but you will get some additional error on the control qubit, because the control qubit swaps into this low coherence mode. Yeah. So one of the things that you can do is when you're doing error correction, you can make your red qubits, the control qubits, as your ancilla qubits, and your blue qubits, the target qubits, as your data qubits. So what this does is that when you do error correction, your ancilla qubit gets all the brunt of the errors, whereas your data qubit is basically untouched and like pristine. And that's what you want in your error correction code, because you repeatedly measure out your ancilla qubits, so it's okay to have errors because it's going to get reinitialized anyways. The thing that needs to persist in coherence and quantum information is this data qubit, which in this gate is going to be the target qubit, which just sits around and does nothing. So it's kind of like the analogy that I try to give is that if you go for dinner, you have this, you have a good time with your friend, but your friend decides to pay. You don't have to pay anything. The guy who pays is the control qubit, which is the ancilla, and the data qubit just has a free lunch or dinner or whatever. So, okay. So before I go into how we characterize the error structure of this gate, I just want to give you the numbers of what we measure, just like a teaser, and then we'll go into the details. So the first thing that you see is that the total error rate of this gate, if you do nothing special, is just 0.5%, which is already pretty good. And again, you can see that there's always this unequal distribution of check between the control and the target. The control pays like 80% of the error, the target pays like 20%. When you look at the other error that happens, which is phase flips, again, there's a big asymmetry. The control pays a little bit more because you transfer into this low coherence mode, but the target is fine. And then the final thing is that the bit flips just never happen. Again, because there's no way to swap population between the two logical cavities, because you're never pumping the nonlinear coupler of those cavities. So this basically, again, never hurts your bit flip rate. So you have this kind of a hierarchy of errors in this gate, which is very, very important. First, you have mostly erasures. Second, you have dephasing, which your error correcting code can correct for. And third is bit flips, which also your error correcting code can correct for, but it just never happened. So again, you don't have to pay the cost of correcting it. Okay, so how do you measure it? So you know the sequence that I showed you initially, how we benchmark this gate, we can just do this, and at the end of the gate, at the end of the sequence, we can just ask a more trivial question, is like, are you erased or not erased? And when you do that, you can just count out the number of shots, how many times this qubit turns up erased or the other qubit turns up erased, and how many times do both turn up erased. And when you fit for that exponential, you can perfectly fit to these rates, and you can backtrack what are the rates of basically erasure for the control, target, and the total. Similarly, you can reconstruct your density matrix, and you can do data analysis on it and find out how many times do you have a z error on either of the two qubits. And when you do that, you can see that, again, the ancilla qubit gets most of the error, and the data qubit, which is the blue points here, like it barely gets any error. Even after 100 CZ gates, you are just approaching like 1% error after 100 gates. So this basically tells you that your data qubit should be very well preserved in this gate scheme. And finally, how do you count whether you have bit flips or not? Is that you have to kind of make one of your qubit in like a block sphere pole state, and then you have to do like repeatedly the CZ gate that I showed you and measure how many times a bit flip occurs. And notice that I did not put one qubit gates on one of the qubits, and this is because of the property that I told you. The single qubit gate breaks the bias between x and z. So if you want to characterize primarily how often x are happening, you have to skip those gates just for characterizing, because otherwise you will always confuse your bit flips for phase flips and so forth. So when you do that, you can count how many times do you, when you start on one of your qubits in 0 or 1 and you do repeatedly your control z gate, how many times does it appear on the other side? And this error rate is so low that it's basically again a bound. And if you do the analysis, you'll find out that it's not actually an excitation going to vacuum and heating, it's just our detection error rate. So even if you are not in the other state, sometimes you will misassign it, right? Just because your measurement is not perfect. So these numbers are basically dominated by this imperfect measurement rather than actual heating. Okay, so yeah, so again, I want to stress that like this error structure and error bias is preserved during the CZ operation as well. Okay, the last one that I want to talk about is like a more non-trivial thing, which again is going to be important in the next part of the talk, is that when an erasure happens during this gate, its impact on your circuit is very benign. What is to say is that if you are having a lot of erasures when you are doing your CZ gate, you will have to check after each gate, are you erased or not? Because if this erasure propagates in a pretty bad fashion, then it can kind of propagate to a lot of qubits if you don't check it after every gate. But one of the neat properties that we have about this gate is that when that happens, that just replaces each of the CZ gate by identity, because it just so happens that the gate just disappears because it is enacted by this cross-current interaction. It needs 2 photons. If one of them is lost, it just switches off. So it's kind of like you're acquiring this phase, and in the middle you just switch off at some time. And that is actually a very, very important property. That means that you don't have to check after every gate whether you're erased or not. You can do a bunch of gates and then at the end check, because either the gate happened or it didn't happen, but nothing more damaging happened. So yeah, and we characterize this by actually initializing one of our qubits in a vacuum state and look at what happens to the unleaked qubit. And what you see is that the unleaked qubit at worst gets just identity. It doesn't get some other operation done on it because you leaked it. And you can again do this, characterize this very accurately by just doing quantum process tomography on your target qubit when you start your control qubit in a leak state. Yeah. So the important part again is that even if the erasure happened in the middle of the gate, it looks like a mixed state between the gate happened and then the erasure happened, or the erasure happened and then no gate happened. So it's kind of like a mixed state between these two, which is important because it's not a Pauli error. And this is kind of a very subtle and important point that makes this pretty powerful. Okay, so this is the error channel, and this is mostly now for like experts, but yeah, if you want to talk about it, I'm happy to talk about it later. Okay, so finally, like, what is it good for? Like, you have this really beautiful structure of errors and like the bias between Pauli and erasure noise. How do you like what is the use of all this? Like, so one of the things that we figured out is that this can actually have a very useful thing, like a very useful impact in error correction, that is to create what we call magic states. But let me talk about this in the next few slides, what that is. So first let me tell you how we plan to build this. So you just build sort of a hexagonal lattice of cavities, and then you attach these couplers, and then you can have like a normal surface code that you would have with transmons or some other qubits using a dual rate qubit. And now again, we make the ancilla qubits as the control qubits, and the data qubits as the target qubit, which is to say that we always swap from the red qubit into the coupler, but never from the blue qubit. And again, the nonlinear elements remain the same that I introduced to you before. Okay, so what can we build? So one of the things that we've built right now is like a 5-qubit quantum processor, which has like this one ancilla qubit, which is connected to 4 data qubits, and this actually encodes a distance to surface code. So the way to read these 4 numbers, 4, 1, 2, is like it's n is the number of physical data qubits you have, k is the number of logical qubits you have in this encoding, which is 1, and 2 is the distance of this code. And what this means is that it has a distance 2, so it cannot correct for any Pauli errors. It can just detect the Pauli error and tell you that there was an error, but it can actually correct for one erasure error and correct for it. And these are the stabilizers of this code. So basically you have 4 data qubits, and there are 3 Pauli operators that have a fixed parity. So you have reduced the Hilbert space from 2 to the 4 to 2 to the 1 because you've fixed 3 of these operators. So that's kind of the stabilizer of this code, and this is the code. And these are the logical code words. So the 0 and 1 logical code words are just some GHZ state in this 4 data qubits. Okay, so the thing that we can do with our qubit already is that we can prepare arbitrary states in its block sphere, in this logical block sphere now. And it also includes the magic state. And let me tell you what a magic state is. So magic state is just one of these special states. Here I'm showing an example of one of the magic states, which is like if you do a quarter turn on your block sphere from one of the poles, you'll get this state. And this is special only because how error correction works. Like in surface code, usually all of the Pauli operators are very trivial to do, but they are not sufficient. You cannot do anything useful because Pauli operators can be simulated in a classical computer. So to do non-trivial quantum computation, you actually need one non-Clifford gate, and and usually how they are done is they're done through these resource states. So you make this non-trivial state which does this non-Clifford operation, and that it gets consumed. And it is such a big overhead in quantum computing that initially when they made estimates, 90% of the physical qubits in the quantum computer was just used to make this non-trivial states. Because these gates are so hard to do in this code that you have to go at great lengths to do it. But now these estimates have come down, but still in the best estimates that are currently available are about 60 to 70% of your total real estate in a quantum computer, like physical qubits, are just used to make this non-trivial resource states. And then they have complicated protocols which take noisy versions of these states and make them into like distilled, high fidelity versions of this state. And those protocols scale like p cube with the noisy probability of a bad state. And what we are trying to claim here is that we can make the initial copy much more high fidelity. So when you go through this protocol, you'll get an even more high fidelity non-trivial state at the end. So basically, you get like this factor of 3, like cubic suppression in your error rate if you start with a better state. If somebody starts with a 10 to the minus 2, they will need to do this distillation to get 10 to the minus 6. But if you start with 10 to the minus 6, you can get 10 to the minus 18, basically. So this has a pretty big impact on how much resources it would take to make a full fault-tolerant quantum computer. So that's basically the application. And now why can we do it much better than others is basically because all of this error structure that I told you about. So let me go into the circuits that are used to prepare the state and try to motivate why we can do it better. So okay, so the circuits that we use to make the state are called exponentiation gadgets. And this is actually nothing new. This has been around for quite a long time. It's actually published, or it is in the most famous quantum computing textbook, Nielsen and Chuang. I don't remember the chapter, but it's there. So it basically says that if you have one ancilla qubit and you do this joint, if you measure this joint parity, entangle your ancilla qubit, and then do a gate on this, you acquire a geometric phase, and then you can make you can do a rotation around this parity operator P in this huge space by just doing single qubit operations on your ancilla qubits. And the neat part about this exponentiation gadget is that the circuit is set up that if this thing succeeds, your ancilla qubits returns to the ground state at the end, and if it fails for whatever reason, not whatever reason, some reasons, it comes up as 1. And then you can throw that shot out. So it's a flag that you can see if your preparation circuit passed or failed. And in addition, because we are using dual rail qubits, every time any of the qubit comes up erased, we can also flag it out. So you have like 6 flags. Each physical qubit has a flag whether it is erased or not, and on top of that, the ancilla qubit has another flag whether it is in 0 or 1. Only when it is in 0 you keep it, and when it is in 1 you can remove it. So you have a lot of these flags which you can leverage and just post-select a lot of this state. And for preparing these resource state, this is actually good. This is not a bad thing, because that's how in quantum computing it works. Like you do all you can do to get a good T state, and then you do that gate using that one state. You consume that state. So it's okay to do post-selection because you are going to use it only one time. Okay, so yeah. So we can tune this theta rotation in the ancilla, and you can create any arbitrary state. So that's why we can do this quarter turn and make this magic state. And again, like I was telling you, it's flag fault tolerant. So when there is an error in the circuit, the ancilla flag will go up and you can remove it. Okay, so yeah. So when you make this P operator ZZXXX operator, which is just one of the stabilizer of the code, you can actually create 0 or a 1 state based on that. So if you tune the theta equal to pi over 2 and you make P the operator as XXX, you can just create this 0 logical state. And I'm going to take the circuit. So this is the exact circuit that is used to prepare the 0 logical state. And if you look at the properties of the CZ gate that we have used, you can see why this is going to perform really, really well. So now I'm going to kind of recall all of this error structure and properties that I just told you about the CZ gate and see how it goes about in the circuit. So you notice that this circuit is basically a bunch of CZ gates. So it's C not here, but just put Hadamard at start and the end, it's CZ then. So the first thing that can happen, the most common error that happens in our system is an erasure in the ancilla qubit, which is because the transmon has lower T1 than the cavities. So the most common thing that happens is that your ancilla qubit gets erased, and that happens at about 0.5% per CZ gate. And when that happens, you just get an erased outcome in your ancilla qubit and you don't keep that short, so it's fine. That error will not determine your magic state fidelity. The second most common error that happens is the erasure in an ancilla qubit, and that is also fine because each data qubit also has a erasure flag, so you will also post-select that error. The next most common error that happens is a Z error, which is dephasing on your ancilla qubit, and this again is flaggable because every time you have a Z error on your ancilla qubit, you can see that you will create the wrong state. It will be 1 instead of 0, and you can again post-select that. So you will not be dominated by actually the ancilla dephasing rate as well. Again, now can you have data dephasing and will that corrupt you? It turns out you also will, you will not face that because any one Z error in this circuit will be decoded by the error correcting code itself. So because remember, I told you that this error correcting code detects one Pauli error and corrects one erasure. So if there is one error in any of the data qubits, that is still fine because that's what this error correcting code is meant to detect anyway. So when you detect that, you throw that short away as well. So the only way you get basically a bad error is that you have a bit flip in your ancilla qubit somewhere in the middle, so you can propagate to 2 phase flips on your data qubits, and that is not protected by the code. But remember, bit flips never happen in our systems because you never drive this transition between the 2 cavities. So this is another error that never happens. So because most of the error that happens are always post-selectable, the only thing that limits you now is that you need to have 2 dephasing errors on 2 different data qubits. That's the only place where this will fail. And that means that we expect our state fidelity to go a square of the data qubit error rates. And the data qubit error rates were like 10 to the minus 4. So you need 2 of them to happen, which is 10 to the 8, but like, okay, there are many gates. So we still expect that we should get like 1 in 10 to the minus 6 of state preparation through this method. And so, okay, so all of this very interesting properties that I told you have some application, but how well do we do in the lab? So, yeah. So let's look how well we can create this X state, the Z state. And if you run the circuit that I just showed you, the Z state, which is the 0 or 1 logical, is prepared with better than 4 nines fidelity already. And this is kind of like the first or second try that we have done in our lab. So these are very preliminary results. But you can see that we can prepare this highly entangled state with very, very high fidelity. And then we can also do this rotation with a half turn, and we can create an X state. And the fidelity is a little bit worse. We are still investigating what is limiting this because from our error structure and the measurements that we have done, we don't expect it to be like only 3.5 nines. We expect it to be at least 4 or 5 nines. So we are still looking into why it is limited to this number, but it's already pretty good. It's already comparable to what you can find in the literature actually. And yeah, finally, you can also just concatenate a bunch of these rotations around different axes, and you can actually create any block sphere spade in this 412 logical qubit by just changing this operator of the parity operator. Yeah, and you can also do actually tomography in a fault tolerant way in these circuits. Yeah, and this is one of the results from basically doing a Rabi oscillation now in this 412 space. So you just change this theta angle in your exponentiation gadget here, the second theta angle here, and it just basically rotates you about the ZX plane, and you can create any state. And you can do that, and you can see these very nice, basically unity contrast oscillations. So they are actually not touching one, but you have to zoom in. The 1 minus number is like 10 to the minus 5, so you can't see it. The markers are much bigger than that, but it is basically a unity contrast oscillation in the ZX plane of the block sphere. Yeah. So again, and you can try to target the quarter turn and see how well you prepare the magic state. Again, it is even worse than the X state, but it is still an open question and investigation of why it's not as well as I was trying to convince you it is going to be. But that's just because it's very new work, so give us some time. Yeah. Okay. So that kind of brings me to the conclusion. So hope I have convinced you that erasure qubits are sort of interesting objects and you can do some really cool things with it. And like for today's dual rail, the error rates are already either better or comparison to the best ones out there. And you can do pretty interesting quantum error correction experiments already with these systems, and hopefully more is to come as we scale up to bigger systems. Thank you.